Alright, class, part 2 is over molecules and compounds. Basically what happens when atoms get together and bond. So again, we're going to start with a little bit of vocab. A molecule is when two or more atoms are bound together. And this is a very general, generic term. A compound is a little more specific. It is when there are two or more atoms of different elements bound together. So you can have molecules that aren't compounds. These are typically gases, oxygen gas, nitrogen gas. But those are examples of molecules that are not compounds. Again, compounds have two different types of atoms, so atoms from different elements. So this is carbon dioxide. It's a molecule and a compound. This is water. It's a molecule and a compound. And this is glucose. That's a molecule and a compound. The way I use the term molecule in everyday terminology, it's a unit. So kind of like when you say, can you hand me one cookie? That one cookie is a molecule of cookie. So that's how I use molecule in my everyday vernacular. It is just a unit of that. So one CO2 is one molecule of CO2. 6 CO2s is 6 molecules of CO2. Be able to read these formulas, pay attention to capitalization. CO2, both capitalized, is very different than C little o 2. This is carbon dioxide. I don't know, that's kind of made up, but it's 2 atoms of cobalt. So pay attention to capitalization. The subscript always tells you how many atoms there are. If there's no subscript, you assume 1. So CO2 means there's 1 carbon and 2 oxygens. C6H12O6 means there's 6 carbons, 12 hydrogens, 6 oxygens. So that's a pretty easy concept. Again, know the difference between compounds and molecules, and know examples of things that are molecules but not compounds. Anytime you make a molecule, it requires a bond to be formed. And, you know, saying bond formation is a chemical reaction is a little restrictive. Chemical reactions are when bonds are changing. So you can be forming a bond, you can be breaking a bond, you can be doing both at the same time. All those are examples of chemical reactions. And the reason atoms bond is to make their valence shells complete. The first type we're going to talk about is ionic bonding. However, just know that most of the time when we're comparing individual bond strength, covalent bonds are stronger. At least one of my test questions will be on how to rank them. You may not get that one because it will be a large bank, but if you were ranking them, covalent bonds are strongest, then ionic bonds, then hydrogen bonds. And I don't know if we cover them in this new book yet, but van der Waals interactions are the weakest interaction. They're not even technically a bond. Let's start with ionic bonding. I already talked about isotopes. I said atoms can change their number of neutrons, and you get isotopes. Atoms, I also said atoms can change their number of electrons, and they're still atoms of the same element. But remember, if you change the proton number, it goes to a different element. It changes the type of element. But an ion has lost or gained an electron. So it is an atom that has changed its number of electrons. It's still an atom of that element due to the proton number, but it is now called an ion. Another way to define an ion, it's just a charged atom. An ionic bond forms when electrons are completely transferred. So one atom lets go of its electron, the other atom grabs it and takes it. So one is donating electrons, one is accepting electrons. And compounds that are held together by ionic bonds, so ionic compounds, all of them are salts. You're most familiar with table salt, but if you look sometimes at active ingredients in drugs, it'll say sodium acetaminophen or something to that effect for the active ingredient. That is a salt of acetaminophen. So anytime you have a compound held together by ionic bonds, those are ionic compounds, and we describe those as salts. One cool thing about salts is they will ionize or separate in water. Alright, so let's talk about sodium. Sodium is in period 3 in group 1. So it has 3 electron shells and 1 lonely electron in its valence shell. It needs 7 whole electrons to fill that valence shell. However, if you look underneath its valence shell, there is a complete electron shell under there. What it actually needs to do, which is a little bit easier, is get rid of that 1 lonely electron, and then it will have a complete valence shell underneath. Chlorine, on the other hand, it's also in period 3, so it has 3 shells, but it's in group 7, so it's so close to that octet rule. It's so close to having a complete valence shell. It just needs 1 electron to complete its valence shell. So it will often take an electron from sodium, like so. And that way sodium has a complete valence shell because it's gotten rid of this electron, and there is a complete valence shell underneath. Chlorine has a complete valence shell because it had 7, and it needed just one more, and it could take that one from sodium and have now a complete valence shell with 8. The problem is the proton number doesn't change, right? So this sodium atom still has 11 protons, but now it only has 10 electrons. So it has 11 positive charges, only 10 negative charges. So it has a +1 charge. Chlorine, on the other hand, has an extra electron, but it still has, let me count, 10, 17. So it has 17 protons, 17 positive charges, but now it has 18 electrons, 18 negative charges. So if you add those up, you have a -1 charge. So we typically don't write the 1, we'll just have a plus sign for +1 and a minus sign for -1. Calcium, that's kind of a weird C. I was halfway to a G there. Anyway, calcium is in group 2. It'll get rid of 2 electrons. So sometimes you'll see it 2+, sometimes it'll have literally 2+ signs, but either way it's notated. Calcium has a +2 charge. Some common salts are sodium chloride, which is what we're seeing in our example, but it's also table salt, so that's why we talk about it. You'll see KCl, which is potassium chloride, and CaCl, which is calcium chloride. But all those are salts. You'll see the potassium and calcium chloride in sports drinks like Gatorade. Notice there are 2 chlorines here. Even when you make ionic bonds, it has to be balanced. So remember, calcium had 2 positive charges. Chlorine only has 1 negative charge. So you need 2 chlorines to balance out the calcium. So there's 1 calcium in that salt and 2 chlorine atoms. Once they form their ions, opposites attract, and those 2 atoms will stick together as long as water doesn't get in the way. Again, when you drop these into water, they will ionize and they will separate. So here's table salt. It's a crystal of sodium and chlorine, I should say. Here's what it looks like under the microscope. And again, it is table salt. So that's an ionic bond. Next are covalent bonds. Remember, individually they are the strongest type in general. There are a few exceptions where ionic bonds are stronger, but in general, covalent bonds are the strongest. Covalent bonds are formed when atoms share electrons. It can be 2, 4, or 6 electrons. That's how many they can share. When they share electrons, however many electrons are shared, count for both atoms. And I'll show you what I mean in a little bit. I'll get to polar versus nonpolar in a little bit. Alright, so here's two hydrogen atoms bound together. That is hydrogen gas. Remember, hydrogen was in group 1, so it only has one valence electron. But it's also in period 1, so it only has one shell. And remember that first shell is full with 2 electrons. So when two hydrogen atoms get together, they'll share their electrons. So these 2 electrons will count for both this hydrogen and that hydrogen. And so their valence electrons are full and they're happy. So hydrogen gas is very stable. Once it's in that form, it'll stay that way unless some energy gets involved. Oxygen gas is the same way, O2, except it shares 4 electrons. So these 4 count for this oxygen and that oxygen. And if you count the rest, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. So their electron shells are satisfied, satisfy the octet rule. When they share 2 electrons or one pair, that's known as a single covalent bond, and we symbolize that as a solid line connecting the 2 atoms. When they share 4, that is 2 pairs, that is a double covalent bond, and we symbolize it sort of with an elongated equal sign, but it's 2 lines that are parallel. And when you can get a triple bond between 2 nitrogens, so nitrogen gas. You can also get a triple bond between a carbon and a nitrogen, and it's symbolized by 3 parallel lines. And if you can guess how many electrons they are sharing 3 pairs or 6 total. But atoms can bind with more than just themselves. So another example is methane. Methane is essentially cow farts. It has 1 carbon and 4 hydrogen atoms, so its formula is CH4. Carbon is in group 4, so it has 4 valence electrons. It needs 4 more to satisfy the octet rule. So it has 4 to begin with. It needs to get to 8. 8 minus 4 is 4. So it needs 4 more to fill its valence shell. Hydrogen atoms, again, are in group 1, row 1. So, or I should say period 1. So they have 1 electron. They need 2 to complete their valence shell. So if carbon needs 4 and each hydrogen donates 1, then you need 1, 2, 3, 4 hydrogens. They'll each share 2 with the carbon. And remember, these 2 count for this atom and the carbon. So these 2 count for the hydrogen and the carbon. These 2 count for both, and those 2 count for both. So we have 2, 4, 6, 8 for carbon, and then we have 2 for each hydrogen. So all 4 atoms are happy. They've satisfied the octet rule. They're no longer reactive. They're now stable. But that's how covalent bonds are formed. They're going to share electrons to complete their valence shell. Now, there are 2 types of covalent bonds. Those are polar covalent bonds and nonpolar covalent bonds. Nonpolar covalent bonds are when they're sharing atoms completely equally, which is more rare than you think. A lot of bonds are polar, and that is when they don't share electrons equally. So they share them unequally. Those electrons tend to spend a lot of time with the electronegative atom than with the less electronegative atom. So we'll look at water in a second, but they make a polar covalent bond where electrons are not shared equally. And one thing that can help you remember it, you would not share with a polar bear. If some polar bear wanted your food, you would back away and let it have it. Polar bears don't share. That should help you know that those electrons are not shared equally. They are still shared though because it is a covalent bond. Okay, so water is one of the best and most classic examples of polar covalent bonds. You can see the covalent bonds right here. So these solid lines here, those are symbolizing the covalent bonds. Now remember when we were looking at the periodic table, I said as we move from left to right, those atoms become more electronegative. Remember, hydrogen is at the top left, and oxygen is somewhere around here. So oxygen is much further right on our periodic table than hydrogen. It is much more electronegative. And also remember I said that electronegative atoms are greedy. They will hoard electrons. So if you looked at the orbits of the electrons, you know, when they're sharing equally, they rotate around both atoms equally. But in a polar situation, a polar covalent bond, it's more like 2 for me, 1 for you, 3 for me, 1 for you. So these electrons will spend more time around the electronegative atom than the electropositive one. So rotate a few times around oxygen, and then once or twice around hydrogen. So you get an unequal distribution. Remember, electrons are negative. They're spending more time around oxygen. So oxygen is partially negative. And the symbol here is delta. It's a lowercase delta in Greek. And it just means there's a difference. It means there's a charge, a partial charge. Since those electrons are spending more time around oxygen, they're spending less time around hydrogen. So hydrogen is losing some of that negativity, and so they are partially positive. So each, let's do the symbol correctly. There we go. So each hydrogen here is partially positive, and the oxygen is partially negative. And remember, those electrons are negative. They're spending more time around oxygen and less time around hydrogen. So the oxygen will be partially negative, and the hydrogen will be partially positive. So if you see an OH bond, those are always polar. Another polar example is carbon to nitrogen. But on the other side, non-polar, of course carbon to carbon, they're going to share equally. And then often when you see CH, it's balanced by NH on the other side. So even though carbon is somewhere around here, it is more electronegative than hydrogen. Often it has hydrogens on both sides of it, so they balance out. So both carbon to hydrogen and carbon to carbon, those are examples of nonpolar bonds. If there's oxygen involved, it's almost always polar. The one exception is carbon dioxide, and it's again because it has oxygen on both sides of it. So the pool cancels out. So I think that's it for yeah, I think that's it for this section. We'll get to water in the next section. That is it for part 2. Next is part 3, which is over water.